Hello everyone, my name is Bhaskaram, and in this video we are going to review MOSFET small signal model. So last video we talked about the large signal model, which is, we talked about the triode equation for the MOSFETs and the saturation equation as well for the NMOS and the PMOS. So large signal model or the square law equation sometimes can be used for, or they're used for biasing the transistor. So like, for example, if you want to park your transistor into saturation, you would use these equations to do so. So basically, yeah, just setting DC operating points. However, small signal model is a little bit different. So when you're dealing with a small signal model, usually your concern is what is the gain of the circuit, or the impedance looking into a node, or switching characteristics of the transistors, and stuff like that. And you use this small signal model mostly in the saturation region. So basically, when the transistors are parked into the saturation region, you have used the large signal model, and now it's time to use the small signal model to see the gain and impedance and all those sorts of things. So let's talk about some of the small signal parameters. The first one, and probably the most important one, is GM, which is the transconductance of a transistor. So one of the goals of the small signal model is to see what kind of drain current change we would see for a small signal change in VGS. So if you think of a transistor as, you know, as a box, as a black box that converts VGS at the input into ID at the output, right? And so what change if we have a small signal change in VGS, how much will the drain current change? That's what we are concerned about when we discuss GM or the transconductance of the transistor. So let's take the saturation equation of the transistor, which you've seen multiple times, and to see uh, how much does ID change based on a small change in VGS. We just take the derivative, right? So we just take the derivative of the saturation equation with respect to VGS. So let me just do that. So here, mu Cox by 2 is a constant, W by L is a constant, 1 plus lambda VDS is a constant, and then 2 VGS, sorry, VGS minus VT, and then 1 minus 0, right? So that's the derivative, and these 2's will cancel out, and then we have mu Cox, W by L, VGS minus VT, 1 plus lambda, sorry, lambda VDS, right? And so that's the derivative of ID with respect to VGS. And we also define it as the GM, or the transconductance of the amplifier. Okay, and so if lambda is 0, or the channel length modulation, or we're ignoring the channel length modulation effect, then we could also write GM as this, right? And so yeah, essentially, the small signal drain current is equals to the GM multiplied by the small signal change in VGS. That's what I wrote in this expression here. So these two are important expressions. So just you should know them all the time, basically. Well, actually, you don't even have to memorize the GM equation, right? Like this one, because like uh, if as long as you know that GM is a transconductance, and it's basically how much it does ID change with respect to a small signal change in VGS, you could just take the derivative of the saturation equation, and you would arrive at this same expression for GM, just like I did right now, right? So you don't have to memorize it as long as you understand what the transconductance is and what it means. So if you look at the ID versus VGS graph, right, where we took the derivative of ID versus VGS and we arrived at the expression for GM. So since it's a derivative, it's what it's telling us is basically GM is just the slope of this curve, right? So this slope, let's say, would be equal to the GM, right? So that's what it is at its core. But here's one thing. Whenever I was taught about transconductance in lectures and in university lectures and in YouTube videos, I was like, okay, I get that GM is a transconductance. I get that it's defined as the change of ID versus VGS, and similar concept for yeah, there's a transconductance for VGTs as well. So like similar ideas, but this transconductance word is such a big word. Like what does it even mean? Why do we care about GM? Right? Why is it defined ID versus VGS? What's the point of it? Right? And all of these questions, I did have them when I was in my second year learning about GM, and like even though I understood it, I didn't really understand it. And like I didn't understand it from the practical design perspective, right? Like if I was in my second year, I was thinking like if I'm an electrical engineer, how is GM going to help me design circuits? So that's what I did not understand. I understood that it's transconductance, but what is the practical application? So here I'm going to give you an example that sort of convinced me about the use of GM and how GM could be used in designing circuits. And so hopefully it also gives you some idea of why GM matters. So let's take an example of this little common source amplifier circuit here, right? So we have a MOSFET with a size of W by L. We have the resistance as a load, and it sets the ID as well, and we have the VGS, right? A DC voltage source that sets the gate of the transistor, the gate voltage of the transistor, and the output is over on the drain of the M1, this M1 transistor. So it's a very simple circuit. And if you know about it, this is the common source amplifier, right? So it basically amplifies whatever is at the gate to the output. So okay, now if I have the W by L fixed, right, and I've decided the value of the resistor and I've decided the value of the VGS, then you would think that we have an operating point that is now fixed on this ID VGS curve, right? Because we have fixed the VGS and we are getting a certain ID. So let's say for the purposes of this example, we have by setting the size, size of the transistor, the resistor, and the VGS, we have chosen this operating point, right? This operating point in green. So that's our VGS. Okay. So now let me add one thing to our little schematic here. Let me say now I'm adding a small signal AC source on the schematic at the gate of the transistor. So this is our AC source. And so really like what's the AC source, right? It could be anything. It could be, let's say, for the purposes of this example, it could be a microphone, right? It's just a sensor that converts sound into a small, usually a very small electrical signal, and you want to amplify it. And to amplify it, you're using this common source amplifier circuit that we have. And so the idea is that you have this small, whatever uh, uh, waveform, the electrical waveform that's coming out of the microphone. Let's say this is like this is me yelling, and this is me whispering, and so the amplitude of that that small signal is changing based on whatever the input is to the sensor, right? And so point is that it's a very small amplitude electrical signal coming from the microphone. And let's say we're trying to amplify it, and then the output goes to the speaker, right? So we're going to convert this little electrical signal into a high amplitude signal, and then we're going to send it to a speaker. Okay. So all right. Now, if I have this small signal source here, just by adding, the circuit was as it was before, but now the only thing that I've changed is that I've added this small signal AC source, which could be, let's say, a microphone, at the gate of the transistor, right? On top of the bias voltage that was the DC bias voltage that's already there. So what quantity has changed for the as far as the transistor is concerned, right? It's the gate voltage. It's the VGS of the transistor that is now changing because of this small signal, because of this, little electrical signal that's coming from the microphone, right? So now in the graph, I could say something like, let's say, this is our, peak to peak of what's coming from the microphone. Let me just erase that little bit here. So the green point was our normal operating point, right? And because of adding this microphone, our VGS wiggles a little bit, and that wiggle is shown by this orange, like these orange lines here. So that's, delta VGS, if you will. That's the change in VGS that's caused by the microphone. Okay, so what will be the ID? What will be the drain current? Because obviously when the VGS is changing, the drain current would change as well, right? So let's see what the ID will be. So let me just draw it out. That's here. This point corresponds to, let's say, this point in the circuit. Okay, and now the ID corresponding to this point would be here. The ID corresponding to the small VGS, the minimum VGS would be here. So if we have, let's say, a sine wave from the microphone that is this large, we would have, or this small, I should say, we would have a change in the drain current, which is much larger. Okay? Like, look at this. It's kind of like amplified, right? And so and so that's the idea. Basically, we were getting some change in ID based on some very small change in VGS coming from the microphone, right? And so because of this, like you can see the high swing in ID, this current is passing through a resistor. And when it passes through the resistor, that change is just going to convert into a voltage, right? So you would have this high voltage swing at the output. And so it would look something like, let me just draw it again. We have this so that's our input, and this is like the amplified version of our output, right? So this is great. That's what we wanted, right? We wanted to amplify the signal, and that's what we have done. All right. Now let me change a couple of things here. Let me change. Let's say I change uh, the DC operating point. So let's say I change the W by L, R, and the VGS such that now my DC operating point is somewhere, let's say here. Okay. Now we are on the right hand graph here. So that's my new DC operating point. Okay. Because I've set the VGS and in a way that this is now the normal operating point. This is the new operating point. Okay. And let's say now we have the same microphone, right? We have the same microphone that is an AC source that adds on top of it, on top of the DC bias. Okay. So let's see what change in current would we get now in this new, by using this new DC operating point. All right. So for the minimum VGS, we would get a current that is here. And for the maximum VGS, we would get a current that is here. Okay. So let's visualize this again, right? For a signal coming from the microphone that is this large, we are getting an ID, a change in ID that is this large. All right. So compare these two cases, right? Like the first operating point, we were getting this large of a current, and the voltage swing would be corresponding to that as well. Here in the second case, our DC operating point is somewhat different, but now our ID swing is not that high anymore, right? It's not that high as compared to the first example. And so the signal is not really amplified that much, which is something that we were not expecting, or something that we were not looking for. We wanted to amplify the signal and send it to the speaker, loud volume, all that sort of stuff. And that's not happening in this second case, okay? So again, you might be wondering, why am I discussing all this? Again, what's the point of GM? Now, let's look at, I told you that GM is just the slope of the ID versus VGS curve. So let's look at the slope here. Let's look at the slope in this condition, which is something we desired. We got a lot of amplification, which was good. Let's call it the good case, and let's call this one the bad case, where we're not getting a lot of amplification. And let's look at the slope over here. Okay. That's the slope over here. So you can see the slope in the first case, in the good case, was much larger. In other words, GM was much larger. In the second case, GM was much smaller, right? And so this is something that, in other words, by knowing GM, you would know how much your signal is going to get amplified, right? So you want to choose a DC operating point where your GM is high enough that you're okay with that level of amplification, and you can send it to your speaker. As far as this example is concerned, right? So GM gives you an idea of how much amplification you would get, and so that's basically where GM comes into use. And you hear a lot of talk about it sometimes. Analog designers would be telling you that we need a higher GM than we are currently getting, or it might be that the devices we have available in the smaller node, we are not getting high enough of a GM, or whatever it might be. GM is something that's frequently discussed, and it's for reasons like this. Sometimes you want to amplify the signal, and GM is important there, right? So this is like a practical example of why GM matters. Now, that being said, 2 points here. One is that in real life, it's not as simple as just sending a microphone signal into a common source. Next time you go to a Taylor Swift concert, it's not like she has a microphone and then it goes right to a common source amplifier, and then some guy is setting the GM and it comes out of the speaker. It doesn't work that way, right? In reality, it's much more complex. The world of audio electronics is it's a complex world, and it's a very interesting world. Lots of interesting challenges in there, and you would have things like op amps, and you would have power amplifiers, and you would have equalizers to add in the effects and all that sort of stuff. All of these things would have very, very interesting analog electronics in them. So yeah, it's not always as simple as like I simplified it to a common source amplifier to make a point. But yeah, and second thing is that this could be any sensor. I just took an example of a microphone, but in reality, this could be like any other sensor, like a photodiode for a camera, right? You would get a very small analog signal, and you want to amplify it, let's say, or you could have a Hall effect sensor for magnetism, or any other gyrometer, or acceleration sensor, or whatever it might be. All of these sensors are just taking a physical quantity and converting it to most of the times it's a very small electrical signal, and you're trying to amplify it. Okay, so yeah, that's essentially a simplistic but practical kind of example to give you a sense of why GM matters. Another important note here is that if you look at the GM expression that we had derived, and if you look at it carefully, we have W over L and we have VGS. So from a designer's perspective, as long as you size your transistor and as long as you set your VGS, your GM is fixed, right? Even though GM is a small signal parameter, the DC voltage at the gate, or the VGS of the transistor, basically the DC value of VGS, and the size of the transistor, looking at this expression, once you set those two quantities, your GM is now fixed. So you want to choose these two quantities in a way where you get a GM that is desirable. right? You would also see like mu Cox and BT, but these are typically not under your control as an analog designer, which is why I didn't talk about them. But yeah, point being that once you set the size of the transistor and you set the DC operating points, your GM is now fixed, right? Or in other words, you now know your GM. Another thing I wanted to say is this is not just one expression for GM. I mentioned two other expressions here for GM as well. The only change is like instead of overdrive voltage in one of these expressions, you have the size of the transistor or the current through the transistor. So this has this expression has ID and overdrive voltage. This one has W by L and ID, and the first one had W by L and VGS, or W by L and overdrive. So you have like different combinations. And so if you're working on problems that in which you have only, let's say, the W by L and the drain current, you could use the third expression here. If you just have the W by L and the overdrive, you could use the first expression here. And if you have the overdrive and the drain current, you could use this second expression here. And also, these three expressions are equivalent. And so if you know one, you can derive the other two, right? And in fact, you don't even need to memorize any of these three. Again, as long as you know the GM is like how much ID changes for a small change in VGS, you could take the derivative right there and basically just you could take the derivative of the saturation equation and arrive at the first expression here. And then once you know the first expression, you can derive the other two. So you don't need to memorize anything as long as you understand what GM actually means. And yeah, that's what I'll say about GM. One side note here is the units for the transconductance or the GM of the transistor is amperes per volt. All right, so now we move on to another small signal parameter called the output conductance or the GDS. So much like the GM, a GDS is also a slope. So what's GDS is basically what is the change in ID with respect to a small change in VDS, right? And so yeah, if you change the VDS a little bit, how much does the drain current change? It's just same concept, but this time we're not doing ID versus VGS. For GDS, we are actually doing ID versus VDS, right? And so same idea, we take the saturation equation for the transistor, and we take the derivative with respect to VDS, and we get this expression that's boxed in. And in fact, you can also make a smaller approximation for a bit more simpler expression. GDS is approximately equal to the drain current multiplied by the lambda or the channel length modulation. So if you have a smaller channel length modulation effect, then your GDS is lower. Okay, and GDS is also reciprocal of the RDS of the transistor. All right. So again, on the graph, if you plot ID versus VDS, which we have done multiple times whenever studying MOSFETs, the graph looks something like this. If it has, channel length modulation, and in the saturation region, if you take the slope of this line here, let's say this would be, this slope would be equivalent to the GDS. Okay. And so you can also imagine a case where lambda is 0. Let's say that case is this one for illustration purposes. So here the slope is 0, and so GDS is 0, and RDS is infinite, which is a good thing. We have infinite output resistance. Of course, it's ideal, but and not necessarily realistic. But you can approach this kind of scenario if you make the length of your transistor longer, and so the lambda effect is much smaller, and your slope is 0 or close to 0, and your GDS is close to 0, and you have a very high RDS. Okay. All right. So now we have talked about GM and GDS, which are two small signal parameters. Now let's talk about the small signal model. All right. So we can represent a simple transistor. Let me just move this around. So for a simple transistor, we have the gate, the drain, right, and the source. And this is equivalent if in a small signal model for a transistor, that's the equivalent version. Okay, that is the simplest equivalent version. So we have a source here that is GM VGS, same GM that we talked about, which is the transconductance, right, multiplied by the VGS or the small signal voltage across the gate and the source. Okay, and yeah, that's the simplest version. But we can add things on top of this simplest variant as needed. So let me explain. Um, let's say now we say that our device is a short channel and now lambda is not zero. So that means GDS is not zero. So now we have to add GDS to our small signal model here. Okay. So that's GDS here. That's how you add GDS to your small signal model. All right, let's go one step further. Let's say now, not only we have channel length modulation effect, we also need to consider the thermal drain noise and the gate couple noise and the transistor. All right, so we can draw that out as well. That's thermal drain noise, IDN, and this is the gate noise, IGN. That's how you can put it on a small signal model. Okay, and again, you can add other noises as well. Whichever ones are relevant to your analysis, you can add them on top of on top of your small signal model. And yeah, there's shot noise, which is important for BJTs, not really for MOSFETs. There's flicker noise, which MOSFETs see at a low frequency. You can add that. It's more of an empirically determined noise as far as I'm aware. No particular expressions to calculate the flicker noise, but yeah, you can add other kinds of noise as well, whatever you think is relevant to your small signal model. Okay, let me go one step further, and let's say this time not only do we have the channel length modulation effect, we also have this thermal drain noise effect. Sorry, we also need to consider the noise, and on top of that, there's also body effect. So our source and body are at two different voltages, at two different potentials, and so body effect is also playing a role. How do we model that in the small signal model? So here the addition we would have is the body or the substrate. So that's VSB. Okay. And then we would also have another current source here, which is GS VSB. So what's this GS? Again, very similar idea. If you take the derivative of ID versus with respect to VSB, you would get GS. So that's just another quantity based on the derivatives. Nothing, just like GM and GDS, there's also GS. Okay. And yeah, again, if VSB is zero, then GS VSB is zero, and that means we don't have a body effect, in which case you can basically ignore everything that I've drawn in pink here. All right. All right, let's go one step further. Now, on top of everything that we have discussed before, now we also, let's say, want to take into effect, or we also want to accommodate or account for the parasitic capacitances. So if you look at the MOSFET geometry, anything really between any implants or any metals, there would be capacitance, right? So there is a capacitance. There is certain parasitic capacitance between gate and source. There is parasitic capacitance between gate and drain, right? Same goes for source and body, drain and body, and gate and body. And basically everything in a MOSFET, you would have some, even if it's very small, you would have some sort of parasitic capacitance. So let's draw it out on a small signal model, right? So this would be CGS. Usually it's pretty relevant for high frequency designs. So CGS is a big one. CGD is also a big one. And then maybe not as important, but There's also CDS. Right? So that's the capacitances within the three terminals. And now we also have all of these three terminals with respect to body. So we would have gate with respect to body. So that would be CUGB. Then we would have source with respect to body. So CSB. And then drain with respect to body. CDB. Okay, so that's the small signal model for one transistor. Now, I don't know about you, but to me, this looks very complex. This looks complex because the fact that this is just one transistor, and remember that this is small signal model is just a tool to analyze analog circuits, right? So we would use this. So for example, when we look at a schematic for current mirrors, to analyze current mirrors, we can replace the two transistors of the mirror with their small signal equivalents, and we can analyze the circuit, and we can see the output resistance and things like that. We can, this would be relevant for differential pairs as well, to get some intuition about differential pairs. This will be important for op amps as well. So yeah, again, like we would be very frequently in later videos, we'll be replacing transistors with their small signal model equivalents and analyzing the circuit. And if, let's say, the one that is in front of you, which has everything included, if that's the model for one transistor, that's, for each one of these nodes, we would have to build up equations, right? So that's a lot of stuff, and this would result in, like, I don't know, 5 or 7 or maybe more equations for just one transistor. And then you would have 5 or 7 or 10 equations for the other transistor, and then you would have to, like, algebraically solve all these 5 and 10 different equations to come up with some final expressions, and that's just for 2 transistors. So this would be like for a current pair. And so if you have a schematic for, let's say, 4 transistors or 5 transistors, you would be doing algebra for, I don't know, 15 to 20 pages, and you would get super complex equations at the end that would not give you any intuition anyway. So the point I'm trying to make here is small signal model. The important note here is that the small signal models are at the core, they're meant to enable designers to do some hand calculation, some hand analysis, and get some idea, get some intuition of what this circuit is doing, right? That's the idea behind the small signal model. And so you want the small signal model to be simple, or in other words, you want to be as complex as it needs to be, but nothing more. So essentially, like even though the last variant of small signal model that you have in front of you, even though that might be the most accurate, it's not the most practical for hand analysis, right? That's too much stuff, and that's too many equations. And your job as an analog, like, if we have too many equations, that's, you could do math for 2 weeks. If you're really good at algebra, that's fine. But then Wolfram Alpha can do the same thing, right? It's not that's not what we want to spend time on when we are doing hand analysis. We don't want to be involved in these super complex equations that take a long time, and the results don't give us a lot of intuition at the end of the day. So it's kind of like a pointless exercise. We want to include as many things as are absolutely needed. Yeah, as many things as we absolutely need to get some idea of what our circuit is doing. All right. So for example, I've seen, like, most of the times when I do my analysis, of course I would have the GNVGS. That you will always have. But if lambda is not 0, if you have a short channel device, you would include the GDS. Let's say I'm thinking about what the noise would look like in the circuit, I would include the IDN as well. If you're doing really high frequency circuits, maybe you want to include CGS as well, right? So, like, I mean, it's possible to just, it's because CGS is a pretty big capacitance. So maybe you want to model that, but maybe you don't want to include all the other five capacitances necessarily with the body and with the with everything included, right? That's what I meant. Basically, a small signal model can be as complex or as simple as you can make it. And this is like for university, it's much simpler because the problems in your exam paper or your assignments will be much more constrained. Usually the professor would tell you that you can ignore lambda, and then in that case you don't model the GDS. They could tell you like ignore the parasitic capacitances or ignore the noise, in which case you can like basically ignore all of that. No body effect, you can ignore the body effect, and you would have a very nice and simple small signal model. Or maybe not. Maybe they'll tell you like use don't assume that lambda is 0, and then you would include the GDS. But nothing. You don't have to include everything else, right? So the problems in university courses are very well constrained, and you would be told what you need to consider and what you can ignore. For real life analog design, it's not as usually not as simple. But again, as an analog designer, it's you should have the understanding of what kind of which one of these things are important. So if CGS is important to you, then include that. If noise is important to you, include that. If you want to take into account the short channel effect, or the channel length modulation, you include that. So like being an analog designer, it's like you build up this understanding of like how much do you want to include in your small signal model when you're doing your analysis, and that's kind of perfecting your hand analysis skill, and that's part of the learning journey for me as well, right? So yeah, basically this small signal model at the end of the day, if it's very complex, it would be more accurate. But if it's too simple, it might be quicker to analyze, but maybe not very accurate. And so that's a trade-off you have there. But again, you have the options as an analog designer to do all these analysis and include as many or as little effects as you need. But yeah, that's the small signal model of transistors and of MOSFET, sorry. And that's pretty much it for this video, and I'll see you in the next one. Thank you. Bye-bye.